this lecture we will look at register allocation, and we will resume optimizations on SSA form when you have done lab 2. So we will first look at something called live variables analysis, which is used to construct the interference graph. And then we will see the shading algorithm for graph coloring register allocation. After that, we will see interprocedural register allocation, which means allocating a variable in several functions. And after that, very nice algorithm from IBM research in Tokyo. So, live variables analysis. The purpose is to see when a variable will be used in the future. And it starts from the definition. For A, that definition is from the beginning of the function, and it ends when it's no longer used in the future. Okay, so A, it's first live with being a parameter, and then it ends here. And then there is a new one here. These ranges of being live are called live ranges. These are two different values, so the, A is not used. This value is not live since it will be overwritten before being used. I mean, it's not used any longer. Okay, so how can we find this? Actually, we start with the use and go backwards until we come to a definition. So what can we have live variables analysis for? We will mostly use it for register allocation to determine if two variables interfere. They interfere if they are live at the same time. Another example of using live analysis is to do a simple form of dead code elimination. A local variable which is given a value, A is set to 1 and then returned. We don't need to save the value in A. Assume we have return B instead. Okay, since A is not live, we can just ignore this definition. Before SSA form, this was the standard form of dead code elimination. With SSA form, we will see a much nicer algorithm. Okay. So we talk about use and def, or gen and kill. It's different words for the same thing. Use and def is the most intuitive. So when we use a variable like A, we use it at, well, obviously, and then we define it when we come to a definition. Okay, not very trivial. But what we will see is that we are interested in the first of use or def within the basic block. Okay, so what we do is to analyze one basic block at a time. First, we do a local analysis for each vertex, and then we combine the information from all the vertices in the control flow graph to see which variables are live at the beginning of a basic block. and then also from that at the end of a basic block. Okay, so what we do, we can do this either in forward direction or in backward direction. As it is written here, it's in forward direction. So we start with the first statement in a basic block. And then we take each right-hand side variable, I mean the operands that we read, and we check if this operand is not in the set def. Def contains all the variables which were defined before they were used in this vertex. Okay, so it was, if it was not defined before, then we add it to use. Okay, and then we do the same, but for definitions. If it was not used before being defined, we add it to def. Okay, so if we look at this graph, we have these two sets, use and def. And well, here there's not much happening in each basic block, but A is obviously defined. In this, A is used and B is defined, etc. It's what we see here is that a variable is never in both of these. Obviously, since it has to be either used or defined first, or it's not in either because it was not mentioned in that vertex. Okay, when we have the local information, we can compute the global live analysis. And this is also an example of iterative data flow analysis. So we start by saying that things change. Okay, so while the data flow information in this control flow graph changes, we make another iteration. So for each vertex, we compute the out. Okay, if this is a basic block, we have the use and def sets, and the out is the set of variables which are live at this point. Okay, and then we have some successors. And in is the set of variables which are live at this point. Okay, so how should we compute out? Well, it's the union of those which are live in the successor vertices. So if we have, for instance, A plus B here, then eventually A and B will be in the inset of this vertex, and therefore it will be in the union of the insets of the successors of this vertex. So it will end up in, they will end up in out W. Okay, now we want to check if the inset of the vertex W that we are processing, if that inset is changing. Because if it does, then we have to redo this. So we make a copy of the old inset, or we just keep the old inset and create a new inset actually. And then we compute the inset. What should the inset be? It's the set of uses union the variables which were live at this point minus the variables which were defined in this basic block. So now we see why we want to have only the first use or the first definition. Okay, so these are the variables which are in the inset. and that means they should be that they are in the inset will be informed, propagated information to the predecessors of this vertex. Namely, when a predecessor uses this. Okay, so if there was a difference between old and in, then we set change to true and repeat this. Just an information in the course EDA N26, there is a project in which you will parallelize this algorithm and use it on a Power 8 IBM machine. And it has 80 cores, and it's a really interesting problem. Okay. So, in which order should we process the basic blocks? Since the information flows backwards, it is better to have processed the successors before we take the union of their insets. So what we do is to use an array, and we put the vertices in post order. So we use this num, and well, we put them in this order. And then we can make this algorithm somewhat faster. So, an example. First of all, we have this, and then we have computed the use and def from the local analysis. And then we have the outset. This is the first iteration. The outset of vertex 5 is empty, obviously, since it has no successor. And then the inset is computed like this, A and B, and they obviously come from the use. Okay, so the inset of 5 is this. And then we can compute the inset, well, first the outset and then the inset of vertex 4, which will be the union of its only successor. So the outset is A and B, and what is defined is B, and what is used is C. So B should not be propagated to the inset of 4, since that value is overwritten here. Okay, and well, A and C, they do reach the inset of 4. And we continue like this, and since there was a change, we do this another iteration. And well, we just update this, and eventually we will find the in and outsets of each vertex.